Okay, great. So is there any question from the notes or anything? So then we can start. So today, the goal for today is to talk about the glorious feathers criterion. That's all we want to do today. Feathers criterion. Okay, so the idea with feathers is that if you have a ring that is finally presented to you, by variables and equations, then it tells you whether or not it is a pure. And in principle, you can even ask a computer to check that for you. But you can do it also by hand. It's not an issue if, of course, your equations are relatively simple. And we will see exactly what simple means. But I don't know if before we get into feathers criterion, it would be wise to do a little recap about the column, the injective hull of the residue fields again. Like there's a few things I would like to say that I didn't say the other day that are very important. So let's start there, okay? So, but first, let's do a little observation about how injective holes change with respect to the residue field. So what is good about so the other day we saw that if we take, let's say, R, maybe it's better to call it as, let me think, but let's call it R, and we take this ring, we take K, and we take power series. Right? So I want to understand what happens if you vary K. So because of that, I'm going to denote this ring as R sub K. So if we have such an explicit ring, I told you that you can define the injective hull of the residue field. So let's call this simply EK. So you can be super explicit about it. It's going to be a direct sum as a K vector space of certain, let's say, negative monomials. So right, you do this. And the only requirement is that all these exponents are all strictly positive, all of them. Okay? So all of these i's, well, they're natural numbers, but they are positive, all of them. Okay, this is the important part. And so the one of the smallest degree, namely of degree D, is the SOHO, right? So the SOHO of this E is K times U, where U denotes this thing. Right? And so this is the SOHO element. It is a copy of K inside of the injective hull. Right? The injective hull has to contain K. And it has to be very tight around it. Okay? So that's your SOHO. Sorry, your injective hull of the residue field. And we also said, okay, what if what I have is a complete local ring? And by the structure theorem, that means that your ring, let's call it AK, is a quotient of R. Right? You may take RK, quotient A. Some ideal. And even if you have that, you can see that the injective hole of the residue field can be computed directly. So we can say that injective hole of K in this ring, right? So what you do is essentially you take the home over R, let's say, from AK to the injective hole, the big one, right? Like let's call that one E, I guess. What is it called? Let's call it what it is. Okay. So you have to do this. You take the injective hole I just told you about, and essentially what you do is you compute the mathless dual of the ring you want to understand, and that's supposed to give you the injective hole of that ring, right? So, but you can be very explicit about what this is too, right? You can just say that these are going to be the elements of the injective hole over RK that are killed by A. Right, that's what this means. Okay, so, and this simple observation has a very important consequence, which actually is an important consequence for further criterion, which is that you can see that, let's say, in particular, so if you have any extension of fields, L over K, right? So what you get is a canonical map from here, but let's say from, well, we have notation over it, forget, from RK to RL. Right? So what varies in the field, right? This is just L power series in a whole bunch of variables, and this is K and power series in the same set of variables. Right? So how do you define that map properly? What is that map? So this map here, by definition, if you want, is the completion So the point I'm trying to make here is that it's not so obvious how you define mass from a power series ring, right? Well, there's a universal property you want to use. So, but the way this map works is that you take the completion of a map that is very finite. So you can define by hand, let's say. So there is the same map between the polynomial rings. Right, this map is very explicit actually, right? This is canonical. So the point here is that since the polynomial ring is finite, this ring here can be thought of as the base change of this other ring over here by L. This inequality here is just not true for power series, because power series are infinite objects. And so tensor products commute with their exon, but they don't commute with products. That's the issue. Okay? So there is this canonical map here, right? We would agree that we have this map given to us. There is no issue with this map. And so what you do is you take the added completion of the ring. In principle, I should say here it is the x1 through xn added completion of that, and that gives you this map. In particular, this map is going to be, the observation I want to make is that this map, because it is the completion of a flat map, it is flat. this map is flat because it's a base change by a flat map. L over K is flat. It is free. And therefore, because it's this base change, this map is flat. It is free, actually. And so you take the base, the completion of that, and that gives you a flat map. So it's flat, but it's local too. So it is local. And so it is faithfully flat. Okay. These are observations that are not so obvious. Okay, you have to argue them properly. Is everyone okay with this? So we have a faithfully flat map between these two rings. And that's all good. And the question I want to ask you is, how do you compare this injective hole versus the injective hole of L? What to do? So the point is that because we have such explicit description of them, we can see, with the naked eye, that one is the base change of the other. Okay? So then, what we get is that, let me put it like this. E or L is going to be obtained by a faithfully flat base change of the injective hole of K over RK. Because you have explicit description, all you have to do to get one from the other is just to change the rest of the field. They're identical, right? So these two things will admit the exact same description. The only thing that matters is the field. So all you have to do is to do a base change. Okay? If you want, like what you can see by the naked eye is that what you do is a base change of the rest of the field, but because the action of the complete ring is built into the structure, it just extends automatically. So this is in a sense tautological. Like it's just that. And so in particular, you see that, well, there will be a canonical map from here to here, right? And what can you say about that map? Because the extension is faithfully flat, in particular pure. It is injective. Conclusion, you can say that this injective hole here is inside. You can think of this as an inclusion. The injective hole over L. And moreover, we can also see that the suckle is preserved under this inclusion because the suckle element goes to the suckle element, right? 1 over x1 xn goes to 1 over x1 xn. The only thing that changed according to the extrude description is what the field is in the direct sum. So, well, I guess I should say something more like, okay, I have K over here, I have L over here, and so this commutes. I think that I have got a typo here in the. Yeah, I made a little typo, I guess. I should change it. Well, I guess it's fine as it is, but it's better this way. So the so-called elements are identified. Okay? So this diagram here is what I need to remember for a few minutes. So let's keep it over here. Again, so you have a wonderful behavior of injective holes of the residue field. and the so-called element is preserved. Remember that it's important to keep track of the so-called element because it dictates whether or not like this a map from injective hole is injective or not. And that's a big deal to know whether or not something is impure. According to the previous class. Okay, so, and actually the exact same thing holds for A instead of R. You know, like here, RK is the power series ring. But because the one for a quotient is obtained from this one, the same thing holds. So moreover, let's say I'm going to put it as an exercise, but it's the same argument, or it just follows from this, to be honest too. So you have, in general, this is inside here as a base change. A L, L, you have K is inside L, and this mapping to the so-called element, right? Here I'm mapping to the so-called. So this is commutative. Okay. Any questions so far with this? Okay, so that's a little recap I wanted to do about injective holes, and it's gonna come up in a sec. So let's just keep it over there. Well, let's talk a bit more about it, okay? Let's write down the important consequence I want to have from this. So the other day, real quick, we mentioned it was an exercise that now if you have an algebra here, theta, and this algebra is pure, then the impurity of S is going to descend to the impurity of R, right? So if we have this, then if S is a pure, then so is R. And this is important because, for example, this is going to give you a whole bunch of examples of impurity. For example, here we can take a regular ring and we just consider, for example, the red elements. So we have that. The question I want to ask now is, what about the converse? Okay. So what about the converse in the case that we were considering over here? Why did we have AK mapping to AL? We saw already, I just mentioned that this is a faithfully flat map, it is pure, right? So remember, this is RK power series modulo A, let's say. Oh, and I haven't said what this is, but this would be AL modulo A. I guess properly speaking, I should mention the extension, right? But if A is generators, has generators, this idea here is just the same generators. That's how it works, you just extend it, right? And so this map here is pure, it's faithfully flat. So pure. Right? So you see the question I'm asking. So this exercise here means that if this is a pure, then this one is a pure. But what about the converse? If this one is a pure, doesn't mean that this one is a pure. In other words, does the residue field play any role in impurity? Right? These two things are the exact same ring, The only thing that changes is the coefficients. Same variables, same equations, different residue field. We just extend the residue field. Does the residue field matter? The answer is no. So then I put it here as an exercise. AK is it pure if and only if AL is pure. And to see why, well, that's essentially right here. Let's see why. I don't know if this little room here is enough, especially for the people on Zoom. Let me try to fit it in here, right? Because what is the meaning of impurity? The meaning of impurity is that if you take the injective hole of K over AK, and you do a base change by the Frobenius of AK, right? The notation is awful. Right? You want to prove that this is injective. That's what impurity means. On the other hand, you write down the exact same thing, but with L instead of K. Let me do over here zoom. I guess that's all the zoom we can get. So you see, but now this one is inside here, right? Actually, you can see that this one is inside here as well. And the subtle element, you know, now I can write down this diagram here. So the point is like this arrow is injected if and only one this one is. And you can see why, because this arrow here is injected, we saw that if and only if the subtle element doesn't vanish. In other words, when you go and look at this one is injective. The subtle element doesn't vanish. And so but you see the subtle element of these two things are identified. So if you want to know that the subtle element here is not killed by this, well, you can go and look at if it's killed when you go this way. Right? Because the subtle element of this one is the image of this subtle element. That's what this diagram is supposed to tell you. Right? So you want to know if the subtle element vanishes here, but then it is the image of the subtle element here. And so the image here is going to be the image going this way. But this one is injected by hypothesis. So these two arrows are injected at the exact same time. But you see the magic of the thing, right? It is because the subtle element here dictates whether or not this map is injective. Remember? This map is injected if and only if the subtle element doesn't vanish. So you have to prove that, but the subtle element here is the image of the subtle element here. That's a remark I started to make today, right? So that's the point. So I hope you can appreciate the beauty of the argument. Like it would be brutal to try to prove that the purity is preserved. You know, no matter what the residue field is, just by pure definition. It's the beauty of this matrix duality and all this injective hole thing that is super explicit and you can track everything down. I also want you to appreciate the type of argument we're making here. Notice that this is a rather computational argument, right? It's just chasing maps, noticing how elements transform and everything like that. You know, this is the computational side. So here you have a very conceptual statement. And you see how we translate it to a computational one, thanks to matrix duality. So you see, we write our experiments in concepts like this, but we prove them computing things like that. So this proof here is an excellent proof to see how this whole business works very generally. Okay. So in practice, if you're writing the paper and have to prove some impurity thing, perhaps, don't try to use brute force. Always try to see if you can complete, perhaps, and apply monthly duality somewhere so that you can compute, right? Okay. That's the philosophy of that. So the only way to appreciate this proof is if you try to do it directly and break your head against it. And you will see the beauty and power of math. Okay. So now we are ready for further criterion. Finally. Took us a while. So what is feathers all about? I feel like I keep pronouncing feathers, like the feathers of a bird. No, but it's feather. Okay, where are we? Here. Actually, there is a version of feathers criterion that we know how to do. What's that? Is that here? No. Okay. So the heart of feathers criterion is the case in which you have a p-basis. Okay. So let's start there. The case in which you have a p-basis, the case of p-basis. So we take R to be S modulo A, where S is a polynomial ring. Well, not a polynomial ring, sorry, a ring that has a p-basis. Regular ring with a p-basis. Let's call it x1 to xn. Remember, this means that the Frobenius of S is super easy to describe. It's just a beautiful direct sum of this form. Would you be mad at me if I just write like this? Okay, you just take this type of monomials, and that's going to give you this decomposition. So the other thing we saw is that this gives you a trace, right? And this was with respect to this basis you got here is the dual element to the one that has like top degree here. So it is in principle dual to x bar, sorry. Let me write it down explicitly. Q minus 1. Right? Any basis gives you a dual basis, and when you consider the dual element to this, it's going to be the generator of this. Sorry, S. Okay. So why is that wonderful? Because we saw the other day that we have an exact sequence that goes like this. And the other way to think about this is that we get a very explicit isomorphism. Well, one thing to notice is that this Frobenius power ideal is a sub-ideal of this column ideal, right? So this portion makes sense. And actually, if you think about this, right, this ring is killed by A. Sorry, this ideal is killed by A, right? Like tautologically, right? If you have, what is an element here? An element here sends A to A cubed. Therefore, any element here is killed by A. Because when you multiply by A, you get inside here, but modulo that is 0. So this is a R module, right? Any S module that is killed by A, sorry, it's an R module automatically. So here you have a map from here that tells you how to compute this thing. And how does that work? You take an element here. What is a good name? Let's call it X. No, X isn't. No. R S. Let's call it S. Okay? And so you do the pairing with that. Oh well, you have to take a portion, right? So we will see that later. This is a form of adjunction. If you have heard that in algebraic adjunction, it's the Frobenius theoretic version of that. Okay, but you have this very explicit thing on how to compute this. And actually, I'm gonna let you think about the following. If you look at that description, let's give ourselves a prime ideal here. So this P, here we're going to be slightly abusive with the notation. So let's take a prime ideal of R. But what is a prime ideal of R? A prime ideal of R is the same thing as an ideal of S that contains A, right? So let me write it down like this. So I'm going to take A over here, and I'm going to take a prime ideal of S, but you know, like it's the exact same thing as a prime ideal of R, right? That's the correspondence between prime ideals of R and prime ideals of S. It's the exact same information. So when I put it here, I'm thinking of it as prime ideal of R, right? For this to make sense, I'm just looking at all those maps in here. This image is inside P, and so you see how it is inside here, right? And so we have this isomorphism. And so I would like to ask you, what do you think this corresponds to? We have an isomorphism. Here we have a submodule, our submodule, so it's supposed to correspond to an R submodule here. Have we given this thing a name? Well, do you see what I'm asking, right? We have this, and what is the inverse image? Well, maybe it's good to give a name. Is it? Well, let's give a name. I'll let you choose. What is a good name? Whatever. Let's put it this. So, what is the inverse image here? So my question is to you, what is the inverse image of this thing? So actually, it kind of follows from the exact same argument as the one to give you this exact sequence. This is going to be Let me check this. AQ, A. So it has to somewhat be related to that, right? It has to be that and something to it, right? So well, what you do is that you take this top part and you intersect with P to the Q. Actually, it's kind of clear that this goes like that. Because if I take a bed that is in here, then when I multiply by P, it's gonna go out by forbiddeness, right? And so then the whole thing lasts inside P. So this direction is sort of like very direct. And what is the most interesting is the other one. That's still true. Okay? So from this, one concludes that now here R localized at P, and you see now here I'm thinking of P as a primary yellow R, is pure if and only if what you want is so what being if pure is gonna mean? So like being is pure, if pure means that let me go a little bit back to have this explanation. It's in principle I make it help, but let me tell you how it works. So what is this purity? Purity means that there is no difference between these two things. Sorry, well, non-being pure at P means that these two things are equal. Like if every map here maps inside P, it's because there is no chance to have any splitting. So if purity means, well, non-purity means that these two things are equal. In other words, it means that the quotient of this ideal by that ideal is 0, which means that the quotient of this ideal by this ideal is 0, which means that this ideal is inside this ideal. Okay? So let me just put the conclusion. It means this. This A is not inside P to the Q. I guess I missed a lot of steps. Well, I saw them in the earth. So, well, let me go through that again. So, right, like I guess what is easier to prove is that not this, but what this means is not. If and only if that's the case, because being not pure again means that the quotient between these two modules is 0. But that would mean that the quotient between this ideal and this ideal is 0. But that just means that this is inside here. Okay, you have to do the whole chain reaction there. But there is no much science into it. And this is what is at the heart of Feder's criterion when you have a P basis. That's Feder's criterion, by the way. It's just that. RP is a pure if and only if you can compute that, or you can verify this. Okay. And that's the criterion. This is what you want to know, and this is how you do it. Okay? When you have a P basis, that's the key hypothesis so far. But I'm going to tell you now how you get rid of that. Well, it's this whole thing over here. Okay. Well, a few remarks. So first remark. And if we have time, we're going to come back to the proof of this because it's very interesting. So the first point to make here is that, well, yeah, Federated criterion is wonderful, but it relies on you computing that column ideal, which is no joke. However, there is a case that happens in practice all the time that is not so bad, which is the case in which A is generated by a regular sequence, or put more geometrically, if R is a complete intersection. So to apply this criterion, one has to compute this thing. And that's no easy task. Actually, right now I'm stuck in a problem in which I need to do that, and I don't know how to do it. But yeah, I'm still trying, okay? But there is a case which is doable, which is what I was saying, the complete intersection case. So, however, if A is generated by a regular sequence, how many elements do we want? Doesn't matter. Is generated by a regular sequence. And here I need a word, let me explain in a sec. A permutable and now we need to look at this. Let me say that way. So what is that? So from the definition of regular sequence, so in principle, being a regular sequence depends on the order of the elements. So it's actually not true in general that if you take this list of elements and it is a regular sequence in this order, that if you permute it, you get a regular sequence. That can fail. So actually, if you have two elements, it's fine. If you have F1, F2, it's a regular sequence. F2, F1 is a regular sequence. But if you have three or more, it may fail. It can easily fail, actually. And geometrically, this can actually why. But there are some instances in which it doesn't matter what the order is. So the two key examples are the case in which the ring is local. So that is the case in which all the F has to go through one single point. Then you have a good control of all of them. So if the ring is local, the order of the element doesn't matter. So if this is a regular sequence, any permutation of them is going to be a regular sequence. The other typical case, which is morally a local case, is the case in which you have a graded sequence. So if we have the polynomial ring, for example, and these are all homogeneous, then it doesn't matter what the order is. Okay, that's what I mean by permutable. It is a regular sequence, but it remains a regular sequence after any permutation of the elements. Okay? So again, you can take the local case or graded case, that's good enough. But there are more cases, right? For example, you can look at, well, let's have a homogeneous case. Then I don't know more examples. Well, but you saw, for example, the p-basis case, right? If you have like a p-basis, the axis of the p-basis, they're a regular sequence, essentially, no matter if you permute the others. No, because there could be units and so on. Almost, okay? Yeah, so there are a whole bunch of examples. So if you have that, then you can compute this thing very easily. So I can tell you generators of this thing. This thing is going to be generated. Well, what has to be here? Well, the elements of a to the q are there, right? So I have to add these guys. F1, Fn to the q. This part here corresponds to a to the q. But now the interesting question is, what else is in there? Well, there is an element that is sort of obviously there, which is what happens if we take the product of all the elements and we raise them to the q minus 1. Notice that this element is in here because if you take this element and you multiply it by any element of A, any F, right? Right. Okay. Well, to test if something is in here, it suffices to show that it takes any generator into AQ by multiplication. Right? So you can see that if you have this element and you multiply, for example, by F1, what happens? Well, F1 to the Q minus 1 is there. So when you multiply by F1, you get F1 to the Q, and therefore you live in A to the Q, right? And the same for F2 and Fn, right? So it is clear that this element belongs there, right? And so here is the delicate question now, what else is in there? In general, very hard. But if you are generated by a permutable regular sequence, then you can finish right there. And that's the magic. This element here dictates what's happening with feathers. So R modulo A, the notation is RP is a pure if and only if all you have to do is to look at this element, right? Because what you do is you kill by A to the Q. So this goes away, and all you have is that. And all you have to do is to compute this product, just a product of polynomials. A computer can do that easy peasy, almost easy. Raise to the Q minus 1, easy. And see whether or not this belongs to P to the Q. Which, if you give me, the elements of P and the generators of P, I can do it too. Right? A computer can test if an element belongs to an ideal, right? For example, using Drucker bases and whatever algorithm, right? A computer can test if an element belongs to an ideal or not. Once you have a Drucker basis and all that, right? But this is very doable. Right? So there is a famous example of this. I don't want to do it right now because I want to move to the proof of the very general version of feather. But let's mention one cute example that everyone loves mentioning. So example. Okay, example. R equals, let's say K, and let's just write down FP. This is an example in which we can apply feathers, right? So, well, so for example, in this ring, this ring here, well, you can see that, well, it's a homogeneous thing and so on. So, well, essentially, you can see that it is regular everywhere in the spectrum except at the origin x, y, z. So that's the only prime ideal that matters here. So you can see that this one is a pure, this ring is a pure equivalent if it splits because it is a finite. If and only if, well, what you do is that you take this polynomial, you raise it to the p minus 1 power, and you have to see whether or not this belongs to x to the q, y to the q, z to the q. So here I'm saying that the only p that matters for this is x, y, z, because this ring is actually regular at any other one. So this is why if purity for this ring means verifying this. And so you do the expansion of this thing, and you kill whatever is in xq, yq, zq, and you see what you are left with, and so on. You do it by hand, it's okay, you have to do it, it's an exercise. And what you realize is that for this to happen, the p has to be congruent to 1 modulo 3. Right, so p can be either congruent to 1 or congruent to, well, I guess p is different from 3 here, right? Because if p is 3, this ring is not even reduced, so it cannot be a pure. Well, I guess this is still true. The statement is still true. But yeah, so you see that there will be infinitely many p's for which this is a pure, and infinitely many p's for which it is not. Okay. So that's a wonderful example. It also illustrates another thing that is very important, which is that the purity is related to something called ordinarity in algebraic geometry. And this is just an example of that. Because here what you have in secret is an elliptic curve. Right? This is supposed to be the equation of an elliptic curve. And so I guess you can say here that this is equivalent to the elliptic curve E being ordinary, as opposed to super singular, which is a bad thing. So if purity equals good in a good way. Okay, that's the moral of the story. Well, one moral is over here that if purity has to do with ordinarity, but the other moral of the story is that you can just go ahead and check that. Just take that, raise it to p minus 1, binomial, trinomial expansion, whatever, chaos, whatever is in here, and see what you have left, if you have something that is 0 or not. And it's going to be equivalent to this. Okay? So it's pretty cool. Actually, as an exercise, I let you do the case. It's a bit harder. As an exercise, you have to do the case in which f is x to the 0. What did I say? I think just to simplify, I think it was something like this. So take d variables, because we can take n variables and degree d. Okay? Take that one and try to see when exactly that's a pure. For which pairs p, I guess triples, p, d, n, this is a pure. And that's going to tell you about the nature of a purity and what it is supposed to represent. Okay? Please do it. It's very fun. So, okay, I'm going to tell you later, if I have the time, why that's true. I wrote down a proof here, if you want to see how this call on ideal computation works. But I think we'd like to move on to something more delicate, which is the actual feathers. Okay? So theorem. If you want, this is the most general version of feathers theorem. It also goes by the name of feathers criterion. it says the following: no p basis, nothing. It says take s comma n. This is very general also because if purity is something that you check locally, so it makes sense to start with a local ring s and k. Let me write that down like this. A regular local ring. Okay. Take any ideal A inside the maximal ideal. So any ideal. Then, out of this, you can get a local ring, which is R modulo what? Sorry. Let's say R equals S modulo A. This is a local ring, right? What is the maximal ideal of this local ring? Well, it is N equals N modulo A, right? And the residue field is K, right? So you have this local ring is a pure if and only if when you compute this this column ideal, it avoids, it is completely different, or it's not contained, in N, no, and it will be N to the Q. So here the key observation, oops, sorry, people of Zoom. The key observation is that I didn't assume that S has a P basis. Okay, I'm not even assuming S is finite. Okay. And so you may be wondering, how do you prove that then? Because what is at the heart of feathers is the P basis, but here you don't have it. What are you supposed to do? A fair reaction would be just to cry because it seems impossible. But it can be reduced in that case, and that's how the proof works. So let's see how you do that. How to reduce to a P basis? You may say, okay, maybe I can use somehow Gauss theorem. But no, it's not defined. So you have to reduce there. And who comes to the rescue? All the so-called nonsense. Sorry, all the injective hole nonsense, all the so-called injective hole nonsense, all that. So that's why I spent a lot of time on that. So how do you prove this? Well, let's write down what we have to prove. So on one hand, we have to verify whether or not this is in here. Right? I have a local ring, and I want to get close to a P basis. Right? What is the first thing that almost has a P basis? Complete rings. Right? Because they look like power series. Right? And so we know that they have a P basis if the residue field is infinite. Right? So the first thing is, okay, I know I can complete. This is fine. And so now this R hat actually, you can think of it as K variables. And notice this is with the completion of S, right? I'm saying that this is the completion of S. And all you do is that you take your ideal and you extend it here. Right? So, well, it's A. Extended, I guess. Where am I saying that to S hat? Right? So our hat is a portion of S hat, and it's literally the same portion, it's just the extension of the ideal. So let's call this A hat. So now I have A hat in S hat. So let's assume that I can do it in the complete case. Let's try to argue that we can reduce it to the complete case. Okay? So if feather were true in the complete case, so assuming feathers in the complete case, this would have to be equivalent to a hat Q, a hat. Notice I wrote here P, I'm so sorry. I meant N. And here we will have to have N hat, where N hat is just N S hat, right? N hat is literally this x1 to xn, right? So what would be the question? Whether or not these two things are equivalent. I claim it is, okay? I claim that. So let me get back to a proof of that in a sec. Let me just look at the time. So you see that, well, this is known, right? This is known. I claim that. So if feathers were true, in the complete case, we would be done, right? Because we want to, this is the question, right? Are these two things equivalent? Well, yes, because this one is equivalent to this one. This one will be equivalent to this one if I can do it in the complete case first. And then I claim that these two things are equal. So these two things will be equivalent, not equal, equivalent. Right? So did you see why I could in principle reduce the complete case, assuming that I may show this claim? Oh yeah. You're right. Almost done, right? Let's say that now we're in the complete case, almost. Modulo defined, right? So, what is my issue? I don't have a P basis. Because my ring is not a finite. Why is it that my ring is not a finite? Why is it that this power series ring is not a finite? What am I missing? It has to do with the K, right? The K is the one killing me here. Because I don't know if K is a finite or not. But why did we start saying today that it shouldn't matter? To take purity. I could, in principle, by the first thing we said today, that I could put here any field I want. Like, K is not perfect, sorry, it's not finite, because it has a very large Frobenius. But how can I get rid of the Frobenius of K? What process can I do to replace K by a field with no Frobenius? Perfection. I can take a perfection of K, right? I can enlarge K. And what is not? I always forget if the curve goes up or down. I think it's down here. So I can go ahead and write here perfection. And write out the same thing. Let me call this ring here now, not S hat, sorry. Not S hat, but let's give it another name. What is a good name? S prime? S prime. S prime. We use a different notation earlier, but you see, all I'm doing is taking my ring and replacing it by a field, by the same ring, but just with the residue field, which is much better. It's perfect. It's perfect. Right? And this ring is just adding all possible p roots in this field. So this thing is a pure. So it's a pure. If and only if that one is a pure. So this is the first remark we made today. If I have a complete local ring, right, I can replace this residue field like that. And if purity remains the same thing, right? So let's pretend that I could prove Feder's criterion here. Let's pretend. So, well, no, it's true. I don't need to pretend anything. It's true because here I have a p-basis, right? We just did that. So here we have a p-basis. We have a p-basis. So this has to be equivalent. Let's give this idea a name. What is it? No, I don't like the prime because I will have to add a prime here, but then I have powers all over the place. Can I just call it tilde maybe? Tilde. Let's use tilde. So this whole idea out here is a tilde. So this would be equivalent to a tilde to the q, a tilde, not inside. Now what I'm going to call n tilde to the q. Where, as you expect, n tilde is just n extended to n tilde. Right? So the question is whether or not these two things are equivalent. Which actually is the exact same question. Here now, let me do this so that you see pull it backwards, the whole thing. Okay. So now the question is whether it is true, but actually I claim that this claim is the exact same claim here, the exact same phenomenon. So I claim this is true. And it's the same thing for both actually. I'm going to tell you instead why. What is the general claim? So these two things are equal. This one is equal, this one is equal, this one not equal, if equivalence. So you see, putting everything together proves that. So modulo, right? Like we can translate these two things. What is the moral of the story? Like we have this line over here of equivalences, which we just verify. If purity deforms very well at their completion and by changing the residue field. Great. All we are left with is verifying that the color condition also transforms very well, but it can be less. So, any questions with this? You see how the proof goes? How you do this reduction? But look, this reduction is possible because of the injective hole and all that. And maths as well, I think that's what I should say. So, okay. Actually, this claim is an exercise here in the notes. Let me break it down for you a little bit more. Okay, so this is the fact, which is an exercise. But I'm going to tell you how it works. So suppose, with the time. It's a local homomorphism. Okay. And so let's take some ideal. And so it extends to an ideal here, right? Let's call it B. That's the game we've been playing, right? Like we have an ideal here, we extend it. Let's call it B just for fun. And so there is an inclusion here that is kind of obvious. So let's suppose that we have this inclusion. I claim that automatically this has to imply that B to the Q, B is inside, well, the extension of N, which is N. Well, it's not N, but it's inside N, right? The claim this is inside N to the Q. If you have an element here, right? What is an element here? It's an element that when you multiply by A, you land inside here. It's all inside here. So, but then if you have if you take an element here that takes B inside here, then that element has to essentially do this. It's just going to be here, but it's inside here. So it's very straightforward. There is really nothing that goes into that. So this is just nothing. Just definitions. There is nothing interesting going on there. Oh, sorry. I meant the other way. I meant the other way. I'm so sorry. Just like I was reading what the exercise says, but the exercise says that's the exercise. So the point is like this one. There is nothing that goes here. Sorry. Yeah. Because if you have an element here, well, it's gonna be here. So it's going to be here, but then you contract and you land inside here. So it's not bad. So this is always true. However, the exercise claims that the converse is true if. So look, we started with a local homomorphism. Remember also that local means that the contraction of N is N, right? Or equivalently, that when you take M and you extend it, it lives inside N. So if the local homomorphism is flat, and so faithfully flat, and so, because the local homomorphism, when it is flat, is automatically faithfully flat. So let's recap. If we have a faithfully flat local homomorphism, this condition here is equivalent to the same condition when you extend everything. So one direction is obvious and the other one is the most interesting one. This follows from a more general lemma. So and that's the one I would like to maybe to do real quick. So this is a particular case of a lemma that has to do with how column ideals behave under base change. So lemma. This is the lemma 419 in the notes. It's a column ideals, and flat base change. So the lemma says that if you have an algebra flat, it's important, flat. So then, look at this. So suppose that you have this column ideal of ideals in R. Okay, so A and B are ideals of R. So A comma B lives in here, and you have this ideal. You can extend it to S, and automatically you get that it's gonna live inside the extension, the column of the extensions. This direction is nothing goes into it. So the claim is that because this is flat, this inclusion is an equality. Then this thing is an equality. And you may be wondering actually straight away, well, I'm claiming this has to do about column ideals and base change. What is the base change, you may ask? Well, the point is that in a flat algebra, base change of ideals and extension of ideals are the exact same thing. So here, when I extend in a flat algebra, I'm base changing the column ideal. So the base change of the column ideal is the column ideal of the base changes of the ideals. Okay, and so that's what is behind this thing. And how you prove this? It's a wonderful proof. And let me stop there with that proof. So I'm going to let you read in the notes the proof I was talking about and how you compute the column ideal in Feder's condition when you have a regular sequence. I don't think we have time to cover it, so I'm just going to let you read it. So how do you prove this? Proof. It's very simple, actually. It has two ingredients. First thing, flatness means that base change and extensions. So you know, like how there is a canonical map from here to here, right? That is reflective. It's just a multiplication part, right? I guess I should have it well. Let's put it like this, right? So you know that, and you know that flatness means that you have an isomorphism. These two objects are the same. Actually, you know that this, how is it called, Baire criterion or something like that? That tells you that flatness means that, right? Extension of ideals is exactly base change of ideals. So that's the first ingredient of the proof. And then you say, okay, how can I understand what column ideals are? So you do the following. You say, okay, let me take A and let me write down generators. For this part of the ideal, sorry, for this part of the proof is where you need, for example, net area. You have to pick up a set of generators, a finite set of generators for A. Actually, if you want, you don't need to assume that R is not even. All you need to assume is that A is finally generated. So you write down generators, and so out of this, you get the following exact sequence. So you have the column ideal you want to understand, right? This is what you want to understand. You know it is an ideal of of R. But it's actually the kernel of a map. That's the point of the proof here. Column ideals are kernels, right? They are kernels. They tell you the elements such that when you multiply by something, they are killed. And so they are the kernel of the canonical map that goes from R to R modulo B in copies of this. So what is this map? This map takes little r, and what you do is that you multiply by every single one of this. R1, R2, blah, 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 RAN. And I'm looking at the kernel of this, right? What is in the kernel of this is an element of R such that it is killing this process, but this process killing here means modulo B. So it means that RA1 is in B. RA2 is in B, right? So literally the column ideal is the kernel of that map. And there you are, right? Because in a flat algebra, kernels are preserved under base change. Right? So if you go ahead and do the base change, well, what you get? Well, you do the base change of this, and I told you what that is. It's just that. So you have V extension S. What is the base change of R is S, and what is the base change of this map is the exact same map. It's just the map where you go to V S times N, and it gives you that. So it tells you that this guy is the kernel of that map. But the kernel of that map, right, it's just BS colon SA. And there you are. So that's why column ideals commute with flat base change, because column ideals are kernels. Deep down, deep down, they are kernels. That's an important thing to remember. Column ideals are kernels. Just put it in your head. Column ideals are kernels. Therefore, they commute with flat base change. And in flat base change, extension and base change is the same thing for ideals. It's this thing. That's it. Okay. And putting everything together, you have feathers. Feathers, you have feathers, like a bird. But yeah. So it's a long involved proof, I know, but it's good to you take your time to digest it. And that's it. That's feathers. That's everything about the purity for now. So next week we're going to start with a completely new subject. But to be completely honest, I still have to decide what it is. It's either canonical modules, local cohomology, cohomology rings, Gaussian rings, because at some point we'll have to talk about it, and I don't know when, maybe next week. Maybe a crash course on that. I don't want to get too much into details. Because the point is that next we want to talk about F regularity. And I think to understand F regularity well, we need to understand the topics here. So let's see what we do next week. So any questions? We're all good? Are you on Zoom? Any concern, question? Okay, so we can continue that next week.